Okay, I think we'll go ahead and get started again. People want to, looks like most people are sitting. Cool. Okay, so this has been a whole lot of lead up. So the first part we talked about sort of hopefully motivating why and when we use machine learning. Now we've talked about how do we get things ready for machine learning. It's time to talk about the actual machine learning process itself. So let's talk about different kinds of models. So we've sort of bounced around this question already. We've heard decision trees, random forests, neural networks. Any other kinds of models people have used or heard about before? So even logistic and linear regression, some people include under the umbrella of machine learning. One of the chat questions is about Bayesian stuff. There are Bayesian methods for machine learning too. Lots of different ways of doing these kinds of things. So the key here is that once we have our data set processed and we've got our training versus validation versus test set, we're ready to start learning one of these models. And so today we're going to talk about three different kinds: decision trees, random forests, and neural networks. We'll show sort of how they work in code, but also I'll walk through up here sort of what's actually happening underneath the hood. What are these methods doing? How are they learning, etc. Neural networks we include especially, how many people have heard the term deep learning in the news? Yeah, so this is sort of all the rage in machine learning. It's this idea of deep learning. And basically all it means is a really big neural network. So it's deep because we make it bigger and bigger and bigger over time. This is the kind of thing that's solving lots of problems for us. Image recognition, speech recognition, all those kinds of things are coming out of this type of method. And so we'll talk about how that works yet too. In terms of popularity of all these things, they definitely shift over time. So neural networks were actually super popular back in the 80s and early 90s. They sort of fell out of vogue though, because the problem was they started getting too big for the computers at the time, and it would take way too long to actually get models that worked very well on complicated problems. So we moved to decision trees, and then Bayesian networks, SVMs, ensemble methods, which is just the idea of combining a bunch of learners together and taking some votes. Random forest fits inside of that. And now we're back to deep learning. So a lot of machine learning is computer science in general, but especially AI and machine learning are very cyclical. Neural networks were originally created in, I think, the 50s or 60s, where somebody took apart a flight simulator and reused the pieces of it and stuff. And then it was popular and then dropped off, and popular and dropped off. So deep learning is the thing right now, but something is going to come take its place yet too. But in the meantime, it's giving us a lot of really cool advances. Okay. So just a little tiny bit of terminology before we move on and get into the weeds here. When I use the term representation, that's just different ways that the computer organizes information. So this is, when I've been saying model, I kind of mean representation. So different ways that we learn and represent that. So a decision tree represents data as this tree structure. That's what we call it in CS. So here we have a bunch of nodes that point to each other, and we can flow through this thing. Random forests are collections of those. Neural networks are these combinations of neurons and stuff. So each one of these different methods, we would say, is a different type of representation, different ways of thinking about the problem and storing what it learns inside the computer. That's a little bit different from the learning algorithm used. So the algorithm is the steps taken to actually create a model in a representation. So just to give an example of this, within decision trees, there's lots of different algorithms for finding the right tree. So ID3 was one of the first one. It's really good if all of your features and your outcome are categorical. C4.5 came after that added the ability to handle numerical attributes. And CART is the one that we see most often. So if in R, in Python, elsewhere, CART is the actual algorithm that's implemented. The key takeaway here is there's a difference between the type of model we're using, the representation, and the algorithm used to create that. And there's lots of options within representations that give us different learned models. So let's talk about CART. So decision trees in general are going to be models that learn how combinations of attribute values lead to different outcomes, or at least are correlated with different outcomes. I want to stay away from the causation language here. Basically, what it's learning is a bunch of rules that determine predictions. So one of the classic data sets for this is deciding if it's a good day to play tennis. That was one of the first data sets used when they were building these models. So it learned rules like if it's sunny outside and not humid, it's a good day to play tennis. If it's rainy and windy, it's not a good day to play tennis. So we can interpret this representation as a set of rules. In terms of what this is made up of, so all the little square boxes here are called nodes in a tree, and those represent different attributes. So the top attribute is the one that the algorithm finds is the most relevant for prediction. So in this case, knowing someone's education level was the most important thing for deciding whether or not they were going to be a respondent to the survey. And then ultimately, from each attribute, there are different possible values, and those represent the different branches you can take coming out of it. So this has different children, because they're underneath this one, and there's one child for each branch. And ultimately, we'll eventually get to the bottom of the tree. These things are called leaves. So it's weird because the tree is actually upside down. The leaves are at the bottom and the root is at the top. But the idea is that once you hit one of these and don't have a branch to take anymore, that's where we make a prediction. That process of making a prediction is just a matter of starting at the top and seeing where you end up. It's kind of like Plinko, if everyone watches Price is Right. Except it's not random. So let's make a prediction here. So we've got a particular person. She has a bachelor's degree, female gender, no landline, but owns a cell phone. So we would feed this into our decision tree, and we say, okay, the first thing that matters is what the most relevant predictor is what's their education level. For this particular instance, it's a 2. So we check, what the tree learned is to check if the education is less than 1.5. That's not the case. 2 is bigger, so that means it's a false. So we go this way. And so now we check gender. So if 0s go to the left, 1s go to the right in this particular instance. Our gender was 1, so we go to the right. We've hit a leaf. That leaf tells us that the class is yes, so we make a prediction of yes. So the rule for this leaf was that any female participant who has a college degree is likely to respond to our survey. If instead we had a different respondent or a different person in our sample, they have some level of college but not a college degree. So again, we check the top attribute. Education of 1 is less than or equal to 1/2, so we go to the left. Now this one checked gender next. Gender was a 0, so we go to the left. We check education again. So we noticed up here there are 3 possible values for education: 0, 1, and 2. Some high school or below, some college, and college degree were our 3. This only had 2 possible ways to go, so we can check it again here. So it said all the 0s and 1s go to the left, all the 2s go to the right. Now that we're here, we can check if there's a difference between 0s and 1s, whether someone has some college or not. This particular person had some college, so we go here, and we predict a no, because we had another leaf node. Sorry. Okay. Step away. We just followed the nodes on the way down. So that's how predicting with a decision tree works. We have this model that's learned. We can look at it, see what kinds of attributes it's considering, and follow it to make a prediction. How do we build the tree in the first place? Any questions about prediction before I go on, though? Okay. So how do I get this tree in the first place? So the goal here is we want to organize all the attributes. So those that are most relevant for prediction are at the top, and all the different paths we follow are going to be different combinations of attributes. If I go back here, all of the instances that went this way to learn this part of the tree were for people who had college degrees. Everyone who didn't have a college degree was used to train this part of the tree over here. So really what we're doing is add an attribute. Once we figure out what the best one is, we split the data, and then we learn on only the subset that satisfies what we've seen so far. So this is the subset of all college graduates, the subset of non-college graduates. We're going to split the data set up every time we pick a new attribute. And what we want to do to decide which attribute is best is we want to pick the one that reduces our uncertainty in what we should predict. What does that mean? So here I have one small piece of our data. This is what got partitioned one way or another. It has 10 instances with a no and 0 instances with a yes. Because all of those have the exact same outcome in them, that's enough to make a leaf node. We're confident in our prediction. Anything that reached here, we've got 10 examples of a no. It's unlikely to be a yes for anybody else. So once we have this set up here where all of the instances have one outcome, we make a leaf. That leaf has the class no because that's what all the instances were over here. And then inside of here, just track some other stuff. We can know how many samples we had that reached that and what their combination of values were. The no's are on the left, the ones are on the yeses are on the right. So we want to be picking attributes so that when we split up the instances, so that all the values that go left or all the values that go right, we want them to be in this kind of case where they all have the same label, same outcome. That doesn't happen too often. Instead, we're going to face a situation where we have multiple of yeses and multiples of no's, or multiples of any of our categories of the outcome. The worst possible case is when they have the same number. So here we're completely uncertain. We have no information that causes us to lean one direction over the other. There's an equal amount of no's and yeses. So if I had to make a random guess, I'd basically just do a coin flip because I don't favor one over the other. We want to try to avoid situations like this. Anytime we have not all of the instances with one label, that's what gives us the nodes of the tree that aren't leaves. But hopefully we never have a node that has this amount of uncertainty in it. Question about certainty? Uncertainty, how we're kind of looking at that? Yeah, go ahead.
You set like a threshold for certainty, like you wouldn't want it to make just a random guess, maybe model off of something that we decided randomly. So if you could set like I only want you to make this decision if you're 60% sure, otherwise like error or like let me know or something like that.
Sure. So yeah, you could say that if none of the attributes, if all of the attributes give us this amount of uncertainty, then just kind of stop because we know the tree isn't going to be very good. You could do something like that. The other way we use a threshold is we don't necessarily make a leaf only when all of the instances have one label. Say that we had like 10 here and 1 here. That might be good enough. We might be certain enough that we can just stop here. Because otherwise what happens is, again, we get to that idea of overfitting, where if we're always trying to make the data set smaller and smaller until we get to the point where all of the instances have the same label, then I'm going to run into lots of cases where there's only one instance in here. And so the likelihood of that instance alone representing a bunch of other ones that aren't in our training set is relatively small. And so we kind of want to avoid those situations. So in practice, we might not only make a leaf in this case, we might make it when there's a certain number, we have a certain certainty. Okay. So the trick is with all this, we're trying to pick the attribute. We would rather pick an attribute that leads to this and not an attribute that leads to this. So the way of deciding that is we want to actually measure how much uncertainty there is, and we want to pick the attribute that gives us the least amount of uncertainty. So to measure uncertainty, we use what's called the Gini index. This is also the variance of a binary random variable. So it's just this py of d is just how many instances in that data have a particular label divided by the total number. This is the proportion of it. So it was 50% for that second example for both. The first one, it was 100% for no's and 0% for yeses. And then we just plug that into here, where we take that proportion times 1 minus itself, sum that for all the attributes. Or sum that for all the possible outcomes, sorry. If we're completely uncertain, in that case where it was balanced numbers 5 and 5, the Gini is going to be 1. And when we were in the first case where all of the instances had the same label, the value was 0. Because when they're all the same, this is a 1, and this is a 1, making this side a 0 for one label. And then for the other one that isn't represented at all, this becomes a 0 times whatever makes it 0. So we're, for each attribute, figuring out if we use this one, what would the genies be, and then pick the one that's lowest. So if I had this really confusing case, say we start out with an equal number of yeses and nos, and one particular attribute, if I make things go to the left, maybe by saying education is less than 1.5, if what goes to the left is all yeses and no nos, then this has perfect certainty, so we have a Gini of 0. The rest of the 7 instances go to the other side. Say they split 5 and 2, because again, there were 5 total yeses and 5 total nos. This has a Gini value as well. So I calculate the average Gini, which is just this number times how many instances there were, and this number times how many instances it had, divided by the total number, and I get some number. Here it's 0.286. The specific number doesn't matter, but it's just something that tells me about all of these certainties inside of here. And if I had other attributes that gave me different average Ginis that were higher than this, then this is the best one, and this is the attribute I would pick at the top. So this is why education got chosen first, because it reduced our uncertainty the most. It took a data set that had almost equal numbers and found a way to make it so that most of the things that went to one side had the same label, and there were similarities on the other side as well. The key is that we're trying to questions about this. I wanted to give a flavor of the math, but not go too much into the details. Okay. So that's how it learns. Basically, that means that, again, when it was building the tree, it would have first picked education as the most important thing. Then on the left, it's only looking at the data where education was 0 or 1. And then it would say, okay, of all of those, how do I split them up? If I look at each attribute, how does that increase our certainty or reduce our uncertainty? And it found that gender was the next relevant thing. And so all the data looked at over here to decide this stuff was different than the data here. Because these are all the ones in the training set where it was a college graduate. These were the ones where it wasn't a college graduate. So it's constantly making the data smaller too. Question?
No, you have a class.
Yes. So if, for example, I had to stop here. So maybe I've got a data point that doesn't have education inside of it. It's missing that value. If that occurred, I could just simply stop here and make a prediction of no. The reason why this one is a no is because when this was trained, there were almost 9,000, there were exactly 9,000 instances plugged in. Over half of them were no's, less than half were yeses, so I have a slight preference towards no. I'm slightly biased that way because that's what my data says. Down here, even though I'm not a leaf node yet, most of the instances that got filtered to here in the training set had a yes. So if I had to stop here, if I didn't know the gender of a person, then I could simply say yes for them, because that's my best guess at that time. So if you needed to stop earlier, you could. Great question. Okay. So, some advantages, special things that are built into this. One great thing about decision trees is it's constantly looking at these attributes and then using the best ones. That means it's actually doing feature selection for us. So if we're using random forests or decision trees, we don't necessarily need to do that feature selection preprocessing step. It happens naturally as part of this. That tree was trained with way more attributes than just the ones considered. The other ones it found just weren't as important for helping with predictions. And so it naturally doesn't use those things. So this simplifies our preprocessing step too. It also, the cool thing is it tells us how we can go back and inspect this afterwards to not only understand how it made predictions and what it learned, but we also can see how important each attribute is. The things that appear higher up were more relevant. The things that were at the bottom are less relevant. So we can use that to understand better what happened in our data. We can also use it to confirm theory. If we thought that these attributes were going to be the most relevant, this gives us evidence that confirms that for us. Or if it finds different things, then that tells us we have something else to go look at, and we can form new hypotheses, run some tests, etc. And lastly, it can handle missing information. So we can do it the way that I just mentioned, where if it hits a node and it can't go on, it uses that node's prediction. What turns out is that decision trees, especially CART, actually leverage correlations between attributes so that if an attribute is missing its value, you can instead use the ones that are most correlated with it. So if say that age and cell phone ownership were correlated, and I'm missing age, then whichever way most people with the same cell phone went when we split the data sets, we can use that for the missing age as well. So different ways of handling it. So correlations don't have to be a problem between attributes. They can actually help us in some ways. Question?
For using decision tree or random forest, is it better to just use all of the attributes available?
I try to start that way too. Unless you've got so many attributes that you know it's going to take forever and you have reasons to throw some out, we might as well just include them all because it's going to eventually weed them out anyway. Great question.
And then next question, can you set the level of the correlation?
What do they mean by level of correlation?
That's all the question says. Sure.
Can you clarify?
You move on and I'll see if she...
If the question was about the correlation between two attributes to know which way to go if they're missing, it tends to form a contingency table and then do a chi-squared analysis for that. If it's categorical. If it is numerical, then it'll just do a straight correlation to figure out how likely they are to each other, or how similar. Cool. Okay. So when do we want to use decision trees as our method? One great reason to do it is when we actually want to understand what was learned. So we can go back to that tree and pull out information like we've been talking about. So that gives us more trust in what it's predicting if it finds things that we expected to be there. If it finds unexpected things, maybe that gives us new knowledge, or it tells us we need to go fix something with our data set and maybe try rerunning it. But lots of different things we can pull out of that. We also use it whenever our predictions probably follow rules. So if some combination of attributes leads to a particular outcome, then this is a good type of model to use. Good for missing data, as we've talked about. And it's great if we might have too many irrelevant attributes because it's going to do feature selection. All reasons to use decision trees. Problems with them, we talked about overfitting already. This idea that if we let it go and only form leaves when it has a couple instances in there, then that's probably something that was some nuance of the training set and not something that generalizes. So there's different ways of addressing that in trees. Second weakness is that, say you get new data, you have a tree already, you get a couple new training instances, there's no way to just add those to your model. We have to instead completely learn an entirely new decision tree. You can think about in the worst case, if it could actually change the top node by slightly changing the way things are filtered, and then that would change everything underneath it as well. Not a likely scenario, but a possible one. So if we get new data, we just have to rerun the entire process to get a new tree.
That decision trees are not generalizable. Like you can't have to retrain on all new data.
Not necessarily, because most of the time it will probably still result in the same tree, meaning it picked up on some general signal. It's just that in the worst case, you could get some weird behavior and stuff. Good question. Okay, so that's decision trees. Let's look at them in the code. Okay. Any other questions first before we do this? Yeah.
So let's say you just want to say cross-validate your model. Different data set. Would you be able to do that?
As long as it has the same sets of attributes, yes. So for all the machine learning methods, if you have trained it on one data set and then want to run it on another one, as long as the attributes are still the same, then you should be able to still make predictions and stuff.
Okay.
Yeah, and as long as the patterns and stuff underlie, then hopefully it still works too. Okay. That's the best case. Cool. Okay. So we come back to the R example. What I didn't describe. Thank you. Okay, here we go. So in the interest of time, I didn't go over this little bit of code that splits the data into training and test for us. For anyone interested, you can check that out. But know that we have a test and a train. Okay, so what we're going to do is there's some code in here that trains three different decision trees using different combinations of attributes, just to see if we get different things. Okay, so we're going to use the rpart library, which is what has CART implemented for us, and we're going to use rpart.plot, which is going to let us actually draw the tree afterwards. So here's my line of code that runs CART to learn a decision tree. So we call our part. Our formula is going to be the thing we want to predict. So in this case, respond. And then the attributes we want to use to predict it. Here we're going to look at only education and gender to start with. So we're going to do the tilde and then add those two things to say, look at these two attributes. We're going to tell it what data set to use. That's our train. We're going to say method equals class to say that this is a classification problem. We're predicting a categorical outcome and not a number. And then model equals true so that we can draw it in a little bit. What I want to predict, which attributes to look at. And when I see that tree, even though I gave it two attributes, it only used one. So it found that education mattered a lot, that people who... Okay, so again, our non-college graduates went to the left, and that is a low number. So... Oh yeah, it just says non-respondent. Sorry, it's already there. Predict non-respondent. And for people with a college degree, they're more likely to be a respondent, so we predict that. It turns out that using gender in this case didn't help make better predictions underneath. We can train another tree using 4 attributes. We're going to add in cell phone and landline now just to see if it changed the results at all. Same code as before, I just changed the attributes to look at. I get a new tree. So again, we're going to look at the same thing at the top, what their education level is. But now I'm going to look for people who don't have a college degree. Gender turned out to be the next most important. Versus for those that had a college degree, cell phone was actually the next most important. So depending on which way we go here, different attributes are going to appear at different parts of the tree. This predicting respondent here is what happens for anyone that owns a cell phone. So the cell phone would be 1 means we go to the right, and they have a college degree. So if those two things are true, we're going to predict respondent for that person. If they don't have a cell phone, then gender mattered a little bit. Men were less likely to be respondents. Women were less likely to be respondents.
Back to the correlation question.
Yeah.
Can you set things in such a way that that you'll only use attributes with correlation coefficient at some threshold? They said 0.8.
Oh, sure.
Or higher.
It's definitely possible to change the machine learning to make it do that. You could add a check in there to say, if that's not the case, then just stop and make a prediction now. In terms of actually running it in like R or Python, I'm not sure if that's a setting in there, but that would definitely be a great idea to have in there. Because if it's not super correlated, then we don't want to follow that information. Great suggestion. Question?
Like along the bottom of the leaves, is the 0.23, 0.30, is that the Gini?
That is a good question. Yes, I believe it's either the Gini or it's the percentage of people that were
respondents. I think that's the case. Because the respondent cases here are all ones that are above 0.5, and the ones that are non-respondents are all less than 0.5. So this is looking at, of all the instances that got filtered at this point, how many of them were a respondent? Good question. The Python version of this shows the Gini in each node, but the R version does not. That'd be nice if it did. And then the percentage is how much of the data got filtered there. So all of the data went into the top node. This node represented 17% of our training set. This one represented 6%, etc. Okay. Then I can, again, train another model that looks at all the attributes. If we want to look at everything, we don't have to list them all. We can just put a period. So again, outcome that we're interested in, which attributes to use. And it learns a pretty similar tree to the one right before. So it turns out that things like region and other things don't matter much for our prediction. We did see that we picked up income group here, but other ones that we originally had didn't matter. Landline never appears, for example. So again, it filtered out those features so we don't have to use them. Okay. Once I have a tree, if I want to make a prediction, we had that test set that was separate. I can call this predict method. I pass in a particular tree. This is the one with 2 attributes. I say to use the test set now. And then again, it's class because we're not predicting numbers, we're predicting categories. That'll give me a prediction for every single instance in the test set. I can then calculate the accuracy, which is just accuracy goes up if it guessed the right thing, goes down if they didn't. That's the same thing as seeing if these things are equal to each other, and then taking the average of all of those. So basically, this sums up how many times they agreed and divided by the total number of them, which is the formula for accuracy. So if I run that for each of the trees, we see that adding some attributes helps us a little bit. So when we went from 2 to 4, we got a 4% increase in our predictions. Adding the rest of the attributes only increased us a little bit. It didn't change the tree very much. And these overall accuracies are decent. So for an unknown respondent, we're guessing right 73% of the time. We'd like to see this closer to 100, but that's a number of us. If I do this in Python, and I'm building my training and test sets, here we're going to use scikit-learn for all the machine learning in Python. I import .tree to give me all the tree stuff. I build a classifier that's of a decision tree. So for each of these machine learning methods in Python, you'll see that we'll call something classifier. Here it's a decision tree, so it's decision tree classifier. And then I pass the training set into this thing, calling fit. Whatever fit returns is the actual tree that was learned. So again, here I'm looking at two particular attributes. And then this block of code is just a way of visualizing the tree. So I get this for my tree. Again, looks at education first. Unlike the R version, this one looks at gender as well. If we go back to the two attributes, this was the R version. This is the Python version. So again, it tells us what we're looking at, what going left and right mean. It tells us the Gini, which is great, and how many samples reach there and the different values of the attributes and stuff. The reason why the R tree looks a little bit different from this one is that if we look here, when we go right, no matter what, our leaf ends up being a yes. And if we go to this direction, no matter where we go, our leaf is a no. So R learned to sort of collapse all of that. That I didn't need to look at the rest of the stuff here. I can simply say, no matter where I go, it's a no. So I can move all of this up and just call this thing a no. Likewise over here, R figured out that these are both yeses, so I can replace this with a yes. It just makes a slightly more compact tree. But they end up making the same predictions. Do the same thing to train with 4 attributes. Again, I get a bigger tree because it wasn't collapsing anything. If I train with all the attributes, this is actually an image. It's just too big to display. So it's huge when you think about all the possible combinations. Question?
Yeah, why are there 2 yes leaves on the 3rd level of the Python tree?
Yeah, so this is, once I looked at gender, it turned out that in both of these cases after splitting it, both of them were still more likely to be a yes prediction than a no. So in this one, of all that got filtered down, 1,500 were yeses and only 1,100 were nos. And here it was even stronger a yes, which is why this is even more blue. So it was 2,400 versus 900. And so the majority for the ones that came in here were still yeses in both cases, but there are slight differences in the propensities there. Okay. If we calculate the accuracies again, we can use .score in Python in scikit-learn to be able to do that. And we see the results. We get very similar to before. About 67% for 2 labels, 72 for 4. But because it's not collapsing things, it's overfitting, and we actually did a little bit worse when we considered all the possible attributes. There's probably some setting in here that I could say to do that collapsing, but it's not the default setting. But similar general trends to what we saw in R. Any questions about decision? Yes?
Is there a way to compare the accuracy rate for the test data and the training data? Because they're only showing the test data results, but not the training data, like how accurate.
Yeah, so you could calculate the training accuracies if you wanted to. Let's go back to the smaller tree. So like here, this would be 2,400 correct and 900 wrong, 1,600 correct, 1,100 wrong, etc. And we could sum all those up, and then eventually be able to do an accuracy off of that too if you wanted to. But usually we only report the evaluation on the test set because that's the generalizability. And I could have instead also here, instead of feeding in test, I could have fed train in again, and it would have told me the accuracy on the training set. Question? Yeah. So what it's going to do then
Is it's going to, when it reaches a leaf,
it's going to predict the average value of the instances that reach there. And when it decides how to split leaves, it's not going to be based on uncertainty anymore because we don't have like a Gini index for numbers. It's going to do, I think, mean squared error is how it's going to decide how to split things. Yes, it is possible for regression. And that's where CART is different than the earlier algorithms, is that it made it possible to do numerical outcomes. Question? Yeah.
Because all of these methods are looking at kind of relationships between variables, would there be a reason or the ability to incorporate complex survey design features like clustering and weighting and stratification?
Yeah. Things like weighting, I haven't seen a good way of doing that yet. Maybe doing some, you get the original prediction and then adjust it based on the weights and stuff might be a way, but I haven't seen too many people working on these things yet, which is a great line of research, actually. That would be really cool to see. Good question. Maybe there are people out there doing that stuff. That would be great for another workshop after Brady's. Cool. Okay, let's do random forests. We've got about a half hour left.
I'm sorry, we have one question.
Oh, yeah, go ahead.
That just came in. What is the null accuracy of this data set? After all, we want the ML prediction to beat this null accuracy. Otherwise, we could just guess based on the initial distribution.
Yeah, null is 60. So there's a 60% of people are non-respondent, 40% are respondents. So if you take the majority one, it'd be a 60%. So it is an improvement. That's a great question. Okay. So far we've looked how to do a single tree. The idea behind random forests is don't learn one tree, learn a bunch of trees, and then combine all their predictions into a single one. The idea being that the wisdom of the crowds. Oftentimes, we're better if we have a bunch of simple decisions that are combined as opposed to one really complicated one. Especially in random forests, we might make the trees a little bit simpler than the single one that we were learning. Ultimately, this allows us to improve our performance and especially reduce the variance in the predictions being made. So how does it work? So we're going to learn a bunch of trees, and then we're going to combine their predictions into a single one. For classification, that just means we take a vote. So we're going to ask the first tree what it predicts. It says yes. The second tree says no. The third tree says yes. So in the end, we got 2 yeses and 1 no's, so we're going to predict yes. So in terms of feeding an instance into each tree, that works the same as it did before. Now we're just using multiple trees. Often we probably have more than 3, so these counts would be a little bit higher, but we're still just going to take the one that has the highest vote. In the regression, where we're trying to predict a number, again, we're going to use averages. So we'll ask the first tree what number it predicts, 1.6, a 2.5, a 1.9. The average of all those in the end is a 2. So my final prediction here is going to be a 2, which is relatively close to 2 of them, not so far from the other. Again, this is some of why it's reducing variance by combining a bunch of decisions together.
Are the attributes on these trees different? I mean, you're not getting the same tree over and over, right? Sorry.
No, that's okay. We had more time. That was the next question. So yeah, if we use the same training set to learn multiple trees, the training process was deterministic, and so each one would come up with the same tree. And so it doesn't help us to have multiple trees if they're all identical to each other. So what we do have to do to make random forest work is give different data to the different trees. Great transition. Thank you. So our solution, there's 2 ways we give different information to different trees. So the first way is we give them different instances. And we use a technique called bagging here, bootstrap aggregating, which is just a fancy way of saying sampling with replacement. So before we talked about sampling our training set as an SRS, a simple random sample, where each instance showed up once. Now we're going to do with replacement, so it might show up multiple times. So we're going to build one training set for each one of the trees and sample with replacement. We're also going to give them different attributes. And so it tends to be that each tree considers fewer attributes than the total number. There's some work out there that shows that a good setting for this is if I have like 9 attributes, I want to use 3 in each tree. If I have 16, I want to use 4. The ideal number is somewhere around the square root of the total number of attributes. That's for classification. If it's a regression problem, then dividing the number of attributes by 3 works really well. I don't know the intuition behind why these are really good settings, but they tend to work in practice. And in R, these are actually the defaults. So it will do this, it'll count how many attributes there are, figure out what kind of outcome you're trying to predict, and do this automatically. So again, we're going to train each tree with different instances and different attributes. So they're all learning sort of localized information for predictions. Otherwise, everything is the exact same as before. We're just building multiple training sets, training different trees, and that's the whole learning process. It follows the same algorithms as before. When do we want to use random forests? We can use it for both classification and regression. It's one of the kind of popular topics right now, other than deep learning. Again, we're still able to pull out the relationships between attributes and labels, which is good. We can inspect the trees and figure out how the attributes lead to different predictions, or how they're related to different predictions. And they're still good with noisy and missing data like trees were. They tend to be better than individual trees. They give slightly higher accuracy because of the wisdom of the crowd by combining multiple trees, and they tend to do a little bit less overfitting in total. Each tree might overfit a little bit more because it's looking possibly at some instances multiple times due to sampling with replacement, and it's also looking at fewer attributes, but that gets averaged out as we look at all the trees together, and so overfitting tends to disappear. The weaknesses of this approach is it takes longer. So before I was learning one tree, now I'm learning n of them, so it takes about n times as long. Now we've got hyperparameters we need to tune. So the number of trees is one hyperparameter, so we can use k-fold to decide the right number for that, the best number for that. We could also change that number of attributes and not use the rule of thumb. That'd be another one. So it takes a little bit longer to find those too. And then the bias in this tends to be a little bit higher too. So if you think about how far it is away from the expected value, it's a little bit more at the benefit of having less variance. That's because each tree has less information to learn from. Again, there's more overfitting in each individual tree. Okay. Questions about the method before we look at the code or the results? Okay. So in R, that is not, one of these times I'll remember. Okay, so here's some code to, instead of training trees, is going to learn some random forests. Again, the nice thing is it's one call, fits back the tree to me, so I don't have to worry about all the internal details. I'm going to use the random forest library to build my trees, and instead of calling rpart to build one tree, I call random forest, and it builds multiple. So what we're going to vary here is instead of the number, we're going to continue to vary how many attributes we pass in, but we're also going to vary the number of trees, just to show that there's some differences as we play with those hyperparameters. So this first one, we're going to learn how to predict respond based on all the attributes, but each tree is only going to look at 3 of them, and we're going to have 100 total trees. And if you're interested in what's being learned, one way to inspect that is to call this importance up here. So I can pass the tree into importance, and it tells me how important each attribute was averaged across all the trees. The biggest number, again, was education for both respondent and non-respondents, so that was the most relevant thing it was looking at. We look at like the regions, those are all super small values, so the trees were, considering that wasn't really helping us. So again, tells us about how good each attribute is, or how useful it is. Do the same thing training with 10 trees instead of 3, and 100 trees but only 1 attribute. They all learn similar in orderings, at least, for the importances. Again, education was the highest, etc. But they give slightly different accuracy. So here's our code then, like with the decision tree, to make some predictions. We call the same predict, test in our random forest instead of a tree, our test set, and it still gives us our list of predictions. We can find our accuracy the same way, etc. So now we see we did slightly better than individual trees. Not a lot better. This data set was one where we didn't see a big boost. It's definitely data set dependent. There's other ones where random forest is a lot better than decision trees, but we didn't really do worse for the most part. So with 100 trees, we got 74% accuracy. If we only used 10 trees, we did almost as well. So those extra 90 trees didn't really give us a ton of benefit. But if we drop it down so that each tree only looks at one attribute at a time, so there's only a single node at the top, that did start to hurt our performance. So we don't want to use too few attributes inside of this. Again, multiple models, slightly different performances. Question?
So when you're reporting for
Mhm.
regression, you often say like this particular variable, like for every 1 unit increase in this variable, and I see an increase in the outcome. Or like, what would you report in getting from this model?
Yeah, this is where machine learning is definitely different. So if you're using a decision tree, sometimes we report the tree itself so that people can sort of make their own inferences from it. With the random forest, we might report something like the importances just to see how relevant each one is. But there is really no way to come back in and say that if I increase education by X amount, it's going to increase my likelihood of the other prediction by Y amount. And it gets even worse when we get to neural networks, where they're going to be our best predictive models. We'll talk about them in a second, but they're very opaque. And so we can't really go back in and know why they learned what they did, and we definitely can't say that this attribute led to this kind of stuff here. So yeah, that is an issue with using machine learning models for sure.
Would record linkage be a good use case for adopting random forests?
It could be, because it's going to look at different combinations of, say, attributes to decide how to link them together and that kind of thing. I'm not super familiar with a lot of research on record linkage, but I've seen neural nets used, and I think I've seen random forests used before as well. So could be a potentially interesting use case. Okay. In the interest of time, there's also the Python example. The code is basically the same. Here's where we get to forests. So now instead of using scikit-learn, we're going to use scikit-ensemble. Then we're going to do similar stuff. One thing I need to note is that when I trained the random forest models in Python, it turns out that age kind of threw off the predictions a bunch. And so dropping age before it got into here actually improved things, which is a little counterintuitive because it's doing feature selection for us. But for some reason, that one sort of hurt a little bit. So dropping it gave us much more similar performance to the R model. Question?
In the third forest, you have 100 trees with each with just one.
Yeah, because they're still going to get different trainings. They're still going to get different sets of instances, so they might learn slightly different splits. You're right that with one attribute, they're probably going to be pretty similar to one another, but there's possible for variance there. Okay, and then final performance here was again 73%, similar to what we saw in R. Okay. Last model. Let's talk about neural networks. This is where some of my research interests lie, partly because these are the popular methods, but partly because extensions of these let us handle way more complicated data than we can do with other types, which unfortunately we might not have time to get to today, but there's a bunch of slides in here with real-world examples in the third section that talk about different kinds of things we can do. And a lot of that is possible due to neural networks. So analyzing what's inside of images works a little bit better in a special kind of neural network than random forests. If we're trying to make sequential predictions, like trying to understand speech as it unfolds during an interview and during a transcript, neural nets are going to be really good for that as well. So this is more of an emerging area that's really, really useful. But enough motivation. The idea behind it is this is kind of a loose attempt by computer scientists and mathematicians to sort of model how the human brain works. Now, I have a good number of neuroscience students in my machine learning class right now, and they're quick to remind me how this is not how the human brain actually works. But the general idea is hopefully there. So the inspiration for this is if you think about the brain, it has about 10 billion neurons inside of it. And each one of those is really highly connected to a bunch of other neurons. So when one part of your brain thinks about something, it shares that with lots of other parts of your brain, or at least other neurons inside of there. And it's kind of significant because when you walk in a room, it only takes about 1/10 of a second to recognize what's happening around you. But each neuron is relatively slow to fire. So it takes, I guess the amount's not up here. But in general, in that 1/10 of a second that you recognize something, a neuron only fired 100 times. And so you think about like computer code, we write thousands and thousands of lines of code to do complicated things, versus here, each neuron's only doing 100 steps. And we're able to do way more complicated things in our human brain than computers can do. So the real implication of that is that a lot of the processing and stuff that happens is parallelized. One part of your brain focuses on one thing, another part focuses on another. And by connecting all these neurons together, they can share information as all that is happening simultaneously. So in neural networks for machine learning, we're going to learn a bunch of individual small predictors that share information with each other, each specializing in different things. They share that with each other, and we hope we get one good prediction at the end. Building this up. This is really closely based to linear and logistic regression that we've, I'm sure, seen before. So linear regression is just the idea that we have a bunch of attributes come in, we multiply each by a weight, we add all those multiplications together, and then we add an intercept term. And then that's our final prediction. We step that up to get logistic regression. Same front part, a bunch of attributes come in, we multiply them by weights, add an intercept, but then we transform that number by passing it into the sigmoid function. So this sum is actually what goes into this little bit here. So it's 1 over 1 plus e to the minus what this thing comes up with. And that gives us a likelihood that the person's going to respond or whatever else we're trying to predict. So the idea in neural networks is that we're going to call this logistic regression a neuron. And we're going to combine a whole bunch of these things and see what the final prediction is. And we combine them in a very specific way. So we're going to have multiple layers of these things that serve different purposes. So at a minimum, we have a hidden layer that contains a bunch of neurons inside of it, each one of them learning something from the attribute values. So all these attributes get fed into each neuron, so each one is a separate logistic regression. They learn different things because we start them with different random weights when we're updating everything. And so each one of these learns something about how these attribute values matter. Then we take the outputs of those logistic regressions and we feed them into another one. And that one is where we get our final prediction. So our decision on whether or not somebody's going to respond or not is not based entirely on just the original attributes, but this gives it opportunity to learn some sort of patterns and things that then boost this thing's performance later on. So one neuron might learn that there's a strong interaction between, say, age and cell phones, like we've mentioned before. Another one might learn that there's a strong interaction between education and income. And using those interactions helps us make the final prediction. We always have some level of hidden neurons that are learning new patterns, and we always have an output layer that makes the final prediction. If we're guessing a number instead of a class, then this is just a linear regression at the end. When we're predicting a binary, yes or no, or two possible outcomes, this is a logistic regression. If we're guessing more than two outcomes, so say we're trying to guess what kinds of things are inside of a picture, then this is a multinomial regression at the end. So the last layer is what we've seen probably before in statistics. The difference is we stack a whole bunch of learning in front of it. And I mentioned before that this is basically unsupervised learning because we don't have outcomes of what these things should be predicting. They're just finding useful patterns. And this is where the supervised learning side of it is. So it's kind of all this learning feeding into itself. But it's as simple as multiple regressions being stacked together. How do we get predictions? We feed an instance in. We figure out what the output of each neuron is here. So we treat it like a logistic regression, see what the outcome is. We feed those, become the input into the next layer. So this thing, again, rather than looking at any of these values, is only going to look at what these things output, and then it's going to make its own prediction. In this case, it output a 95%, so it thinks it's super likely that the person is to respond. That does mean that these models are a little bit different than decision trees and random forests. Before we had a singular prediction, yes or no. Here we're getting a confidence value, just like we do in a normal logistic regression. Questions about the setup for neural networks? Yeah.
How does this get implemented with missing data on some variables? Like,
Yeah, it does not like missing data. So that's one of the weaknesses of this. Is if you look back at what happens, like each one of these neurons is multiplying weights times the inputs. If the input is missing, it doesn't know what to do. So you basically have to either impute or filter them out ahead of time.
and
That's
so
a plus for decision
multiple
trees.
imputation, you're talking about replicating this process over multiple data sets. And then,
Yeah, it gets messy.
Yeah.
That is a real world weakness. Okay. Other questions about the setup? Okay. How does training work? So ultimately, the goal here is to find the right set of weights in every single neuron. So each neuron is multiple weights times all of their inputs. We have to train all of those. And so it's kind of messy and kind of more complicated than the other methods we looked at so far. This takes a little bit longer to run. Ultimately, we set it up as a minimization problem. The idea being we want to minimize the amount of error in the final predictions, and we use that to decide how to update all the weights. The general idea is that we're going to look at each instance, update the weights, look at another instance, update the weights. And we're going to keep repeating that process over and over and over. So different from decision trees and random forests, both of those looked at the data set once. Here we're going to keep feeding the data set in to keep updating the weights until either they converge or until we're happy, we've gotten a good enough accuracy, essentially. The algorithm, most of the approaches for this rely on a technique called backpropagation, which itself comes from something called stochastic gradient descent. This is a way of minimizing something. Give a little bit of intuition on how that works. Say I have a function that I want to minimize. So to find where this is smallest, useful information is what the slope of the line is. So I can make a guess and say, oh, I think maybe the minimum is here, but that is a pretty big slope. So slope is how much this function is changing as the input to it changes. And so slope is equal to derivative from calculus. So I'm not going to make this a big calculus lesson. Even my students don't like that very much. But the general idea being that the derivative here helps us, the slope. If I'm at the minimum, the derivative is 0. If the function's not changing, I can move in either direction and my output doesn't change very much. If I'm far away, then I have a bigger derivative. And so I can use that to help guide me towards where the function might be minimum. The idea here, let me actually put the animations on. Okay. So I've got this particular function. It has this form up here, just a parabola that's been shifted a little bit. And that has a derivative. And so the idea being, I'm going to try to guess where the minimum is. I'm going to pick some value, doesn't matter where. I happen to choose this spot. So what I do is I figure out, okay, what's the slope here? And I use that slope to move myself towards the minimum. So the slope here is a 4. So I'm going to make a new guess based on that old value. I'm going to take the old guess, subtract off the slope times some learning rate. This is a hyperparameter that I choose. Here I chose 0.25. It's a smaller number, so I'm less aggressive in how much I'm changing each time. So 3 minus this thing gives me 2. So my guess has moved from here to here. I've gotten closer. I repeat the process. I calculate the derivative at 2. I plug that into my update formula. Old equal or new equals old minus learning rate times derivative, and I get 1.5. So if I repeat this a bunch of times, I get closer and closer and closer to the spot where it's minimized, which is 1. The key intuition just being that if I know how to find the slope of this function, I can minimize it. There's some risk, though. This learning rate hyperparameter is really important. So, example, say that I used a bigger value of 0.75. Now, if this is my initial guess, my next guess actually ends up on the other side of the minimum. So I've overshot and ended up over here. It's still okay, though, because I'm closer to the minimum than I used to be. And so the next time it's going to overshoot a little bit this way, overshoot a little bit this way, but eventually it's going to fall into there. So I like to use the analogy of skiing for this. So you're trying to push yourself down a mountain. How hard you push off is that learning rate, but we're trying to find the bottom of this all the time. Maybe you hit the valley and go up a little bit, but eventually, hopefully, you get to the bottom. Too big of a learning rate can make this process take longer. If I had used a 1 for the learning rate instead of 0.75, I would have gone from here to here and back and forth. And I would have constantly bounced between those 2 points, and I never actually would find the minimum. Even worse, if I used a value more than 1, I would overshoot more and more each time and move as far away as possible from the minimum. We need to be kind of careful when we choose learning rates. The rule of thumb for this is to use something like 0.1 or 0.01, pretty small values. The smaller my learning rate, the longer it's going to take for me to find the right neural network weights, but hopefully I eventually get there. Training the weights follows this kind of process, but not for one weight, but for all of them, which is kind of complicated. What ends up happening is it uses a lot of higher order math, especially using matrices for anybody that's seen that kind of stuff before, to speed some of this stuff up. We are looking at more instances, more times, using this kind of method versus decision trees, so it's going to take a lot longer. We can offset that by, in computers, the thing that draws pictures on our monitors, the graphics card, actually it's specialized hardware for doing matrix math. Deciding what gets drawn and how your windows move around and that kind of stuff when you move the mouse is actually just a bunch of matrices being multiplied and added together. And so we can take those parts and use them for machine learning stuff instead of for drawing, and we get way faster performance. So the rule of thumb here is that if you run this stuff on a graphics card that does this matrix math, you get about a 30-fold speed increase. So what used to take a month only takes a day, and what used to take a day takes less than an hour. And if we had a little more time, I've got a demo of that where it's actually more than a 30-fold speed increase when we're doing it on this particular data set. It was actually closer to 100, I think. So you can get some pretty big boosts from this. Okay, rule of thumb of when to do this. Computer science people will tell you to only use neural networks. I'm not a huge fan of that because I like being able to inspect things afterwards. But this is what's being used by deep learning and driving all the advances. So Siri, Alexa, all those kinds of things have deep learning models inside them, really big neural networks. And lots of other self-driving cars are all driven by this as well, and some other applications too. Part of the reason for that is there's some theoretical math that says that basically anything you want to learn can be learned by a neural network. The downside is you might need it to be infinitely large. But in terms of why we like this, you want to do this the more complicated your problem is. If it's not a bunch of simple rules that if these two combinations of attributes happen, then it's this particular outcome. But if it's lots and lots of difficult patterns, neural networks are going to pick up on those better than trees and forests. And also, they're going to tend to give us greater performance. Regardless of how good the decision tree or random forest does, oftentimes a neural net will do a little bit better, but we're sacrificing our ability to understand what was learned in the process. So that's one weakness. Another is that this has more hyperparameters. We need to figure out the right learning rate, as we talked about, the right number of neurons in each layer, the right number of hidden layers, a whole bunch of other things. That's more time for training than we already were doing. Again, they're opaque. And then as we sort of had the question about missing data, these need more pre-processing than the others. So because we're multiplying weights, this is when we absolutely have to do one-hot encodings, and we have to be able to make sure there's no missing data and other things going on as well. Questions about neural networks as a method? Yeah.
The reference to deep learning, that just pertains to the number of layers. Like, is there a rule of thumb for when we're just doing like a simple neural net? And what's the threshold where I'm officially doing deep learning?
Yeah, so that's a good question. When you start getting into the 5 to 10 region, I think is when deep learning starts to pick up. The bigger difference is there are special types of neural networks in deep learning. So when we want to do this for image, and there's some slides on this later, but when we want to do this for image data, we don't want to look at all the parts of the image at the same time. We want to focus on little pieces of it. If I'm trying to find a cat in somebody's photo, I don't need to know the entire image to find the cat. I only need the part that has the cat. And the information around the cat is more relevant than all the other parts. So deep learning models, a lot of it is
those kinds of specialties, that there are more layers in order to handle sort of those kinds of spatial relationships and stuff. Another one is if we're dealing with sequential data, how does things unfold over time? Say you're trying to make predictions about people's days based off of GPS data you've collected, or you want to be able to, again, predict whether they're going to finish a survey based on what they've done so far during it. Those things unfold over time, and so you're going to need more and more layers to be able to look at all those time points and stuff. Okay. General rules of thumb for a problem. If I care about transparency and understanding what was learning, or I care about speed, decision trees are great. If I care more about performance, or I want to be able to update my model when I get a little bit more information, then neural nets tend to be a little bit better. And there are some examples in the code of neural net usage. So I've used the MXNet library in R. Anyone that's trying to install this, especially on a Mac, it's not the easiest thing to get going. You have to install some external libraries outside of R and that kind of thing. The challenge is in R, at least in my opinion, the libraries aren't as good as they are in other languages. So scikit-learn, in the example in Python, is a lot more flexible and tends to perform better. Part of the problem is that you have less control over how the R methods are learning, and the default settings don't work on a lot of data sets, so a lot of times the model just doesn't converge, and you can't use it at all. That's what kept happening when I was trying to do it on this particular data set. MXNet gives me a little more control and behaves a little bit more like the Python libraries do, and so that one gave us better performance here. Just a little caveat. One other quick thing that had to happen here is that, especially in neural nets, but other methods as well, that class imbalance thing becomes an issue. When you have lots more of one outcome than others, here it saw that 60% of the outcomes were non-respondent, and so it tended to learn to predict just non-respondent all the time. So to combat that, I made a slightly smaller training set that threw away some of the non-respondent examples so that I had an even number of them, and that gave me a lot better learning performance. Again, the Python libraries didn't need that. They did okay otherwise. But if you start getting these really big skews, you might want to do what's called undersampling in order to get fewer of them. Also, it needed, just like in Python, we needed to have the attributes separate from the labels, which is all this code does. But then, again, it's one line of code to learn a network. And I can do the same thing if I want a different one. This one has 2 layers instead of 1, etc. So feel free to take a look at those. The examples on the Python as well. It does everything. So. But yeah, I think it's 1 o'clock. Are there any questions about anything? I'm glad we got through sort of the 3 different methods, and we're able to talk about sort of the full pipeline. The only little bit we didn't get to was different ways of evaluating. What are recall? How do you calculate accuracies on individual labels? But hopefully that's pretty straightforward too.
You do have a slide.
I do, yeah. So if we go in, okay, so here's the last part about evaluating performance. This is a little more detail on how accuracy was formed, what recall and precision are, and then some additional thoughts on additional applications. So if I want to do the open-ended text coding, what are some differences I need to be able to do? So how do I handle text data versus the other stuff? And then if I want to work with images, how is that kind of neural network different from some of the other ones? So there's extra stuff there for you. If you have any questions, please feel free to email me. Happy to help. So thank you, everybody.